Alrighty guys, so in today's lecture we're going to continue learning about balancing chemical equations, but we're going to be adding one more thing to it. So we're going to be learning about how to write the state of matter notation. Now state of matter is just a fancy way of saying if something is a solid, liquid, or gas. So before we learn how to write that in our chemical equations, let's kind of review what states of matter are. Okay. So we learned before that atoms are microscopic units that make up all matter. Now the key thing to remember is that atoms, they're constantly moving. So if you guys take a look on the right here, we have this little simulation from a site called PhET, and we have a solid. Okay, so we know it's a solid because this, whatever this is, it's keeping its shape, right? This object is keeping its shape. But if you notice, all of the atoms that make up the object, they're still vibrating. So everything that you see that's solid, so like your desk, your phone, those are all made out of atoms. And even though it looks like they're not moving on a microscopic level, all of the atoms are moving. They're vibrating, but they're able to keep their shape. Now what we need to remember is the amount these atoms move, it depends on how much energy that they have. So if we add heat energy, so if we heat this up, we're going to be adding heat energy. And if we do that, you're going to notice that the atoms start moving a bit faster, they start vibrating more, and as we heat it up, they start vibrating to the point where they break apart and they turn into, in this situation, a gas. So depending on how much energy these atoms have, it tells us what state of matter it's going to be, whether it's a solid, liquid, or gas. So if we want to compare, going back to the solid, solids, the atoms are vibrating a little bit, but they're able to keep their shape. But if we look at a liquid, the atoms are vibrating a little bit more. And so they're not really able to keep their shape. They're not all flying around yet, right? There's one random one right there. But they're still able to keep their shape. But when we turn it into a gas by adding more energy, all the atoms are moving around, they're flying around, and so the state of matter that something is in depends on how much energy that they have. And depending on how the atoms are moving, an object can have different characteristics, right? We know the difference between solid, liquid, and gas. So the key point here is that when we go from a solid to a liquid, it means we're going to add energy. Okay, we're going to add energy. When we go from liquid to gas, we're also going to be adding energy. Okay, and so an easy way for us to think about it is this entire trend right here. We're going to be increasing the temperature. Okay, and this is pretty obvious. We're all familiar with this, right? If you have an ice cube and you add energy, you're increasing the temperature. You turn it into a liquid, which is water, and if you add more energy by boiling it, it's going to turn into water vapor. And the opposite is true as well. You're going to, once you lose energy, if a gas loses energy, it turns into a liquid. And if a liquid loses more energy, it's going to turn into a solid. Now, there are some things beyond this. There's actually 5 states of matter, but we're not going to be talking about the extremes here. For the most part, we're going to be talking about solids, liquids, and gases. So that's all you guys need to know, at least for the scope of this class. And as we go this way, we're going to be decreasing temperature. All right? And so just a last visualization of what the states of matter, how the atoms move. Solid, they're moving, but they're able to keep their shape. Liquid, they can't keep their shape, but they're still moving and they're still pretty close together. But in a gas, they are not able to, atoms are not able to keep their shape, and they're just moving around. They're not really stuck to each other. Now, there is one more thing we need to remember, and it's that sometimes in chemical reactions, which is what we're going to be going back to, the molecules are sometimes dissolved in water. So a lot of times when we do chemical reactions, we're going to have chemicals inside of water. So we're going to have water, and then we're going to have chemicals dissolved inside of that water. When a chemical is dissolved in water, it's known as aqueous, okay, which means it's dissolved in water. And we note that by writing AQ. So I forgot to mention it earlier, but solids, the symbols that we're going to be using is S, obviously, liquid, L. I'm going to do it cursive just so it doesn't look like a 1. And the notation for gas is G. And for when something is a chemical is aqueous, we're going to denote that as AQ. Okay, so keep these four things in mind, solid, liquid, gas, and aqueous, because that's what we're going to be using in our balancing chemical equations. All right, so let's continue doing balancing chemical equation examples, but this time with state of matter notation. So in today's assignment, you're going to have the same directions as this. You're going to balance the chemical equations, and you're going to include state of matter notation. So we said earlier that's going to be the solid, liquid, gas, or aqueous. Okay? So before we do the state of matter notations, let's balance it first. So here it tells you that As2O3 and H3ASO3 are solids. H2O is a liquid. But before we do the notations, let's just balance it first. So this first step is we're going to balance. Step 1, balance, and then we're going to write the state of matter notations. Now, we talked about this earlier, but we're going to split up the equation between the left side and the right side, the reactants and the products. And we need to make sure that we have the same number of each element on both sides. Now, if you notice, on the reactant side, we have AS. It's not going to be A and S. The element symbols are based on capital letters. Okay, so AS, we have O, oxygen, and then we have H, and it looks like we have O again. So let's count these up. How many AS's do we have? We have 2. How many oxygens do we have? We have 3. We have 3 right here, but we also have 1 right here next to H2 in H2O. So we're going to have 4. And how many H's do we have? We have 2. We have 2 right here. All right. So we talked about this last time, but we're always going to have the exact same types of elements on both sides. So we're going to have an AS here. Excuse me. We're going to have an O here, and we have an H here. So let's count them up. How many H's do I have? I got 3. How many AS's? I have 1. And how many O's? I have 3. Okay, so if you notice, everything is messed up, right? Nothing is balanced out because we have 2 AS's, 1, 4 O's, and then 3, and then 2, and then 3. So let's start with the AS's. Okay, for AS, it looks like there's more on the left side. That means we have to add another one to the right side. So I'm going to add an AS, but I can't just add it like this by itself. I have to add the entire molecule. So I'm going to add H3ASO3. And if I do that, I have to redo all the numbers here. Okay, how many AS's do I have? I have 1, I have 2. Okay, so this number is going to change to 2. How many oxygens do I have? I have 3 that I had before, and now I have 6. How many H's do I have? I had 3, and now I have 6, because 3 plus 3 is 6. Okay, so now if you notice, the AS's are good. There's 2 of each, but the O's and the H's are still messed up. And so it looks like we need to go to the left side and add more oxygen and hydrogen, right? Because there's more oxygen and hydrogen on the right side now. Okay, so I'm going to go to the other side, and I'm going to add more oxygens and hydrogens. So if you notice, oxygen is on both molecules. There's oxygen here, and there's oxygen here. But if you notice, we need to fix up oxygen and hydrogen. So we're probably going to want to add more H2O, right? Because if I add more of the As2O3s, I'm going to mess up this AS number, and I don't want to do that. I don't want to imbalance it again. So we're probably going to be adding more H2Os. Okay, so I'm going to add one more H2O. If I add one more H2O, how many oxygens am I going to have? I'm going to have one more, right? Because I have 3 here, 4, and then 5. But I want to get 6, so that means I'm probably going to have to add one more. So if I add another H2O, how many oxygens do I have on the left side? I have 3 in this molecule, 4, 5, and 6. So now I have 6, which is exactly what I want, because I have 6 oxygens on the left side and on the right side. Now I added H2O. That means I changed the number for hydrogen as well. So how many hydrogens do I have? I have 2, 4, 6. So I'm going to have 6, which is good because I have 6 here and 6 here. So these are balanced out. And if you notice, everything is balanced out now. So let's write the balanced chemical equation. Okay, so for the balanced chemical equation, we're just going to copy down As2O3, right? We didn't add any of this, so there's just a 1 in front of it, but we can ignore the 1. So that means I'm going to have H2O3 plus, how many H2Os do I have? I have 1, 2, 3. So I'm going to write a number 3 in front of H2O. So I have 3 H2O produces, how many of this compound do I have? I have 1, 2. So I'm going to write 2 H3ASO3. Okay, so there we go. We balanced it all out. This chemical reaction tells us that we need 1 AS2O3 with 3 H2Os to produce 2 H3ASO3s. Now we did the balancing part, but now we have to do the state of matter notations. Lucky for us, this is really easy. All we need to do is look at whether or not these molecules are solid, liquids, gases, or dissolved in water. So it says that As2O3 and H3ASO3 are solids. So all I'm going to do is right next to it, I'm just going to put an S inside of parentheses. Again, this is going to be a subscript. This is going to be a small letter, just like how we have them here. These are subscripts. So we're going to put an S next to As2O3, so that one's done. H3ASO3 is also solid, so we're going to put that. Now that one's done. And the last one, H2O, is a liquid, so I'm going to put a cursive L just so we know that it's a liquid and not a 1 or something like that. Alrighty, there you go. That's exactly what you need for today's assignment. You're just going to need to balance out the chemical equations like last time, but you're just going to have to add whether or not they're solid, liquid, gas, or aqueous. Alright, so not too different. We just need to add what state of matter they're in. Okay, let's do another example. And again, same thing as last time. If you feel pretty confident trying these on your own, I recommend that you pause the video and try it, and then double check with me once you're done. But if not, that's okay. I'm going to go through it step by step. Okay, so we have this equation, and so what I'm going to do is draw a line just to separate them, and I'm going to write down how many of each element we have. We have Na, so I'm going to write Na. I have H, and I have O. And so if we count these up, we're going to see that we have 1 Na, we have 1 sodium, we have 2 hydrogens, and we have 1 oxygen on the left side. Now when we go to the right side, on the right side we're also going to have Na, we're going to have H, and we're going to have O, but we're going to have different numbers. Okay, so I have 1 Na, I have 3 H's because I have an H here, and I have 2 here. They're split up. So I'm going to have 3, and then I'm going to have 1 oxygen. So it looks like here the issue is going to be with our hydrogens, right? I have more hydrogens on the right side than I do on the left side. So if I have more hydrogens on the right side, I'm going to have to add more hydrogens on the left side. So let's add a hydrogen on the left side. So I can't just write an H by itself. I have to add the whole molecule that H is in. So I'm going to add H2O. If I add H2O, I no longer have 2, I have 2, 4, right? Because I have 2 different H2O molecules, so I'm going to have 4. But since I added another H2O molecule, I changed the number of oxygens that I have. So I'm going to have 1, 2 oxygen. So this is going to be a 2. It looks like we haven't fixed the hydrogen problem, and we've actually made another problem because now oxygen is not balanced out either. But it looks like I have more hydrogen and oxygen on the left side than I do the right side now. So I'm going to have to add some to the right side. So we can try to fix the hydrogen by adding either NaOH or H. But there is a better choice that we can make. If you notice, they both have hydrogen, but now we have a problem with both of the oxygens, right? So I want to fix hydrogen and oxygen. But if you look at this molecule right here, NaOH, it has both oxygen and hydrogen. So it has all the elements, or 2 of the elements that we want to fix. So we're going to add that one instead because it's going to affect both. So I'm going to add NaOH. If I add NaOH, I change the number of NAs that I have on the right side. I'm going to have 2. I'm going to change the number of oxygens. I'm going to have 2. And I added another hydrogen, so I have 4. So once we do that, we're going to notice that we have the hydrogens balanced, right, 4 and 4, and we also have the oxygens balanced, 2 and 2. Okay, lastly, we need to fix up the sodiums, the NAs, because now I have more sodiums on the right side than I do on the left side. But this is a quick fix because sodium is just hanging out by itself. So I can just add a sodium, and that's going to give me 2 sodiums. And now these are good to go as well. So everybody's balanced and happy. So let's write the balanced chemical equation. So we have Na, so I'm going to copy down Na. But I'm gonna write a 2 in the front because I have 2 of them. I'm gonna copy down H2O, and I have 2 of them, so I'm gonna write that down. Produces, I have 2 NaOHs, and then we're gonna do H2. Alright, so we're almost done. We just need to write the state of matter notation now. So Na is a solid, so I'm gonna write an S next to Na. H2O is a liquid, so I'm going to write liquid. H2 is a gas, so I'm going to write G next to H2. And NaOH is dissolved in water, which means that it is aqueous. And remember, the notation for aqueous is AQ. So there you go. Super simple. This would be your final answer. Alright, we're going to do one last example, and then we'll be done for today. So moving on to the last example. Again, if you feel confident doing these on your own, feel free to pause the video and try it out. But if not, I'm going to go over this step by step as well. So again, we're going to start off by balancing this chemical equation. So I'm going to draw a line again. And then let's count how many of each element we have. We have Fe, and then we have parentheses OH3. So if you notice, we have Fe, O, and H. So we're going to have iron, we're going to have oxygen, and we're going to have hydrogen. Okay, which means we're also going to have iron, oxygen, and hydrogen on the right side as well. Okay, so let's count up how many of each of these elements we have on both sides. So on the left side, we're going to have how many Fe's. There's no number behind it, so I'm going to write just 1. I have 1 Fe. Oops. Yeah, 1 Fe. Alright, so when it comes to the oxygen and hydrogen, they're inside the parentheses, which means that everything inside the parentheses is going to be multiplied by the number on the outside. So there's 1 oxygen, right, because there's no number here, and there's only 1 hydrogen. So that means I have 1 oxygen, 1 hydrogen inside of the molecule. But there's a 3 on the outside, so that means I have to multiply it. So I'm going to have 3 oxygens, and I'm going to have 3 hydrogens. Okay, moving on to the right side, how many Fe's do I have? I'm going to have 2. How many oxygens? I have 3 here, and I have another 1 here, so I'm going to have 4, and I'm going to have 2 hydrogens, because there's a 2 right here. So we have all the numbers now, and it looks like everything is messed up, so let's start with Fe, because that's the one at the top of the chart, right? So it looks like I have more Fe's on the right side, because I have 2. And I only have 1 on the left side. So I'm going to add another Fe. But in order to do that, I need to add the whole molecule. So I need to add FeOH3. Okay, so once we add that, let's count them up. How many Fe's do I have now? I have 2 Fe's. I have 2 irons. So I'm going to have 2. How many oxygens do I have? Since I added another one of the same molecule, I just need to double this. I have 6. Same thing with hydrogen, I have 6. So I have 2, 6, 6. Now it looks like I have more oxygen and hydrogen on the left side, so I'm going to have to add oxygen and hydrogen on the right side. Okay, so we can either add this molecule, Fe2O3, or we can add H2O. But if you guys remember, there's always a better choice we can make. If you take a look at what's not balanced, the oxygens and hydrogens are not balanced. So if we add more waters, if we add more H2O, we can be working on both the oxygen and hydrogen problem at the same time. So let's add an H2O. If I add H2O, how many hydrogens do I have? I have 2, 4. Okay, so I'm almost at 6. So if I add another H2O, I'm going to have 2, 4, 6. So I'll have 6. And then if we count the waters, we have 3 right here, 4, 5, 6. So we're going to have 6 oxygens, and if you notice, voila, everything is balanced out. Okay, so we're good to go. Now all we need to do is write the balanced chemical equation. So I'm just going to copy down FeOH3, and it looks like I have two of them, right? I have this one right here, the one we started off with, and then I added one, so I have two, and that produces, we have Fe2O3, so I'm going to copy that down. There's no number, or there's only one of them, so we don't need to write a number, a coefficient. And then we copy down H2O. How many do I have? I have three of them, so I'm just going to write a 3. And then lastly, we just need to write the state of matter notation. So it says that FeOH3 and Fe2O3 are dissolved in water. So if they're dissolved in water, we know that they're aqueous. So we're going to write AQ next to both of them. And then for H2O, it says it's a liquid, so we're going to write an L next to it. All right, there you go. That's going to be the answer for this problem. So this is basically the same thing that we did last time. It's just some more practice with balancing, but you're just adding one more thing as you write the state of matter notation. So I'm in the Zoom call right now, so if you have any questions, make sure you guys let me know. But good luck on your assignment, guys, and we'll see you next time.